একি বন্ধনে জড়ালি গো বন্ধু কোন রক্তিম পলাশের স্বপ্ন মোর অন্তরে ছড়ালি গো বন্ধু।
We have come a long way from the days of Thomas Alva Edison. Today, using digital technology, sound recording is as simple as breathing in and breathing out. The best part of it is, using these ubiquitous gadgets of everyday use, the recorded sound is acceptable enough to be used on professional platforms. It is easy to store, easy to share, and can be copied again and again and again with practically no generation loss.
All this is possible because in the process of digital recording, the sound signal is converted into a binary code, that is, a series of zeros and ones. Each 0 or 1 is a bit. 8 bits make a byte, and 2, 3 or 4 bytes make a word. The bytes can be stored on a hard disk, or a pen drive, or a CD, or even a magnetic tape.
The music CDs available in the market are read-only CDs or CD-ROMs. We can play these on a computer or on a CD player, but we cannot erase or re-record on the same medium.
A CD can store up to 74 minutes of music. So, how much digital data is stored on a CD? In all professional digital recordings, the sampling frequency is kept at least double the highest audio frequency in the signal. Since the highest audible frequency is 20 kHz, the minimum sampling frequency for all professional recording is 44.1 kHz. That means there are 44,100 samples in each channel of the music. For stereophonic recording, the music will have 2 channels. By this elementary arithmetic, we see that the number of bytes stored in the channel is 783,216,000.
A CD is a fairly simple piece of plastic, about 1.2 mm thick. During manufacturing, this plastic is impressed with microscopic bumps arranged as a single continuous and extremely long spiral track of data. A thin reflective aluminium layer is sputtered onto the disc covering the bumps. Then, a thin acrylic layer is sprayed over the aluminium to protect it. A cross-section of a complete CD looks like this.
This has basically 2 layers of plastic which is sandwiching 1 layer of metal which is very thin. Let's see if we can break this CD. We might see. If you look at it from a closer distance, you can make out that there will be layers of plastic and the metal, which is a very thin, very thin metal. The track pitch of the data is 1.6 micron, which is very less, and the bit length or the digital data which is being written here is done by a laser which has 780 to 790 nanometer diameter. So you can understand how thin that layer, the diameter of the laser is.
The track is approximately 0.5 microns wide, with 1.6 microns separating one track from the next. And the bumps are even more minuscule.
The elongated bumps that make up the track are each 0.5 microns wide, a minimum of 0.83 microns long, and 125 nanometers high. A nanometer is a billionth of a meter. The incredibly small dimensions of the bumps make the spiral track on a CD extremely long. If we could lift the data track off a CD and stretch it out into a straight line, it would be 0.5 microns wide and almost 5 kilometers long. To read something this small, you need an incredibly precise disc reading mechanism. Let's take a look at that.
It rotates in a circular motion, and the head, instead of tracking from outside to inside, which used to happen in case of LP records, it tracks from inside to outside, and it maintains the same speed. So, when you insert a CD, if you play track number 1, if you visually look at the CD, it will rotate at a slower speed, since it's reading the inside circles. And when if you play, for example, track 10, you will see the CD has started rotating much faster, because the reading head or the recording head has gone to the edge. So, the speed has to be maintained according to that.
The drive consists of three fundamental components. A drive motor spins the disc. This drive motor is precisely controlled to rotate between 200 and 500 revolutions per minute, depending on which track is being read. There is a laser and a lens system to read the bumps. A tracking mechanism moves the laser assembly so that the laser's beam can follow the spiral track. The tracking system has to be able to move the laser at micron resolutions.
The hardest part is keeping the laser beam centered on the data track. This centering is the job of the tracking system. The tracking system, as it plays the CD, has to continually move the laser outward. As the laser moves outward from the center of the disc, the bumps move past the laser faster. This happens because the linear speed of the bumps is equal to the radius times the speed at which the disc is revolving, or RPM, or revolutions per minute. Therefore, as the laser moves outward, the spindle motor must decrease the speed of the CD. That way, the bumps travel past the laser at a constant speed, and the data comes off the disc at a constant rate.
It's worth taking a peek into the genesis of this complex process demanding accuracy of the order of nanometers. The 1960s were the era of long-playing vinyl records. The diamond stylus spiraled from the periphery to the center and picked up the music coded as bumps on the surface. On repeated playing, the stylus got blunt and the record surface lost its bumps, degenerating the music. James Russell, like all music lovers, was frustrated by this wear and tear. He tried making the stylus with different material like the cactus thorn. He also realized that the constant friction generated static electricity. These charged discs would attract dust, and then the record would move in the same groove. The vinyl records could also get bent in the heat. Sitting at his study table, Russell was struck by an idea. He thought to himself, what if the stylus is something weightless, something insubstantial, yet razor sharp? Does something like that exist?
Yes, of course it does. The first functional laser had been designed by Myman in 1960. This consisted of highly focused, coherent beams of light. Was it not possible to use a laser beam as a stylus? It would not be very difficult to design a device where, instead of a stylus, a laser beam would track the grooves of the disc spirally. But then a laser beam would not feel the jerks like a physical stylus. And without generating any jerks and jolts, how could the bumps get decoded into sound once again?
Russell looked hard at the lamp atop his study table and got another bright idea. A laser beam can distinguish between bright and dark spots. Russell was familiar with digital data recording in punch card or magnetic tape form. He saw that if he could represent the binary 0 and 1 with darkness and light, the laser beam could track it successfully and the data would be decoded into music in no time. Such a player could play the recorded music without ever wearing out. But then the music had to be digitized and coded into binary digits. Russell's predecessor, Max Matthews, had already done that. He had written a program called Music just for that.
Digitizing the music brought in another great advantage. A large amount of data could be stored in a small space. So Russell could design small discs that would record entire symphonies. He called them the compact discs. After years of work, Russell succeeded in inventing the first digital to optical recording and playback system. He patented it in 1970. He had found a way of recording onto a photosensitive platter in tiny bits of light and darkness, each 1 micron in diameter. A laser read the binary patterns, and a computer converted the data into an electronic signal, which it was then comparatively simple to convert into an audio transmission.
CDs became the rage of the decade. Gramophone players soon became museum pieces. Beethoven symphonies on a CD, that must be really grand. But what's this? What happened to the music? Has a sponge soaked up the music?
We can actually see that the layer which is being sandwiched inside the plastic, the metal layer, has completely worn off. It has completely eroded. Now, these compact discs are by the company which is a German company, and obviously they are not being tropicalized and they are meant for European weather. Now, when you are bringing a CD like this in a country like India, which is very hot and humid, there might be material expansion and contraction, for which there might be leakages which might be, and from that leakage all the moist air might have crept in and eroded or completely oxidized the metal layer that on which the data was written. And as a result, you will see that you can see through the thing, and all this metal that is in between is completely like oxidized and it's become brown.
That means CDs can also be vulnerable to the wind and the weather. Digital recording of sound still remained outside the purview of the amateur musician. Musicians were on the lookout for a system with which they would be able to record their live performances digitally.
To satisfy this demand, Sony introduced the digital audio tape in the market in 1987. In appearance, the digital audio tape, or DAT, is similar to the audio cassette. It uses a 4mm magnetic tape enclosed in a protective shell, but it is only half the size of the audio cassette.
এটা 1992 সাল থেকে আমাদের কাছে এসেছে। এইটা দিয়ে আমাদের মেন উদ্দেশ্য ছিল ফিল্ডে গিয়ে রেকর্ডিং করা। এটা আমরা আউটডোরে কিছু ট্রাফিক অ্যাম্বিয়েন্স রেকর্ড করেছি, সেটা একটু শোনাচ্ছি। যদি আমরা একটা ট্রেনের সাউন্ড রেকর্ড করি, ট্রেনের দিকে আমরা এক সাইডে যদি দাঁড়িয়ে থাকি, ট্রেনটা দূর থেকে এলো আবার চলে যাচ্ছে, সেটা আমরা কিন্তু এফেক্ট পেতে পারি। এটা সুবিধা ছিল খুব। স্টিরিওফোনিক রেকর্ডিংয়ের এই মানে সাধারণত টেপ রেকর্ডার এইসব থাকে না, এইটাতে কিন্তু আছে।
As the name suggests, the recording on the magnetic tape is digital. The binary coded audio signal gets recorded. Hence, it requires less space.
A DAT recorder can handle different sampling rates. 32 kHz at 12 bits and 32 kHz, 44.1 kHz or 48 kHz at 16 bits. Since each recording standard uses the same tape, the quality of the sampling has a direct relation to the duration of the recording. 32 kHz at 12 bits will allow 6 hours of recording onto a 3-hour tape, while 96 kHz sampling at 24 bits will allow only 90 minutes from the same tape.
DAT machines running at 32 kHz sample rate transport the tape at 4.075 mm per second. DAT machines running at 48 kHz and 44.1 kHz sample rates transport the tape at 8.15 mm per second. Included in the signal data are subcodes to indicate the beginning and the ending of tracks. These subcodes also allow you to skip a section entirely. This makes indexing and fast seeking easy. 2-channel stereo recording is supported under all sampling rates.
পুরো ভিডিও ফরম্যাটের মতো এটা ভেতরে টেপটা পুলিং হয় তো অনেকটা জটিল ছিল ভেতরের ব্যাপার কিন্তু সাউন্ড কোয়ালিটি খুব সুন্দর ছিল এত ভালো কোয়ালিটি সাউন্ড যখন আমরা আগে স্পুলে রেকর্ড করতাম স্পুলের পরে কিন্তু ফাইনালি প্ল্যান হয়ে গেছিল আর দ্যাট ক্যাসেট ছাড়া রেকর্ডিং হবে না ওটা দিয়ে সবাই রাখতো
The technology of DAT is closely based on that of the video recorders, using a rotating head and helical scan to record data. This prevents DATs from being physically edited in the cut and splice manner of analog tapes or open-reel digital tapes.
এই ইন্টারভিউ রেকর্ড করার জন্য খুব ভালো এটা সাউন্ড কোয়ালিটি এত ক্লিন আর কোনো নয়েজ নেই টেপ হিস নেই যেরকম আমরা একটা ক্যাসেটে রেকর্ড করলে ক্যাসেটে একটা টেপ হিস থাকে অনেক সময় ক্যাসেট পুরনো হয়ে গেলে কোয়ালিটি লস হয়ে গেলে আরও বেশি হিস শুনতে পাওয়া যায় কিন্তু এতে কোনো টেপ হিস নেই
DAT is used professionally due to its lossless encoding, which allows a master tape to be created that is secure and does not induce tape noise or hiss into the recording.
গৌতম ঘোষের সিল্ক রুট যেটা ডকুমেন্টারি ফিল্ম উনি করেছিলেন এই দ্যাট অনেক ব্যবহার হয়েছে এবং ওনার নিজেরও একটা সোনি পোর্টেবল দ্যাট রেকর্ড আছে ওটা দিয়েও উনি করেছেন আর চিত্রবাণীর এটা দিয়েও অনেক ব্যবহার হয়েছে চিত্রবাণীতে এটা আছে বলে আমরা এখনও ফিল্ডে নিয়ে যাই কিন্তু ম্যাক্সিমাম জায়গায় লোকে এখন সেই ল্যাপটপ রেকর্ডার হার্ড ডিস্ক রেকর্ডার নিয়ে ওরা আউটডোরে গিয়ে রেকর্ডিং করে
DAT machines lost their popularity after the 1990s. In the 21st century, music can be recorded directly onto the hard disk.
It would be interesting to note that any format which is being closed or shut down, it's given a funeral. So DAT had its funeral 4 years ago and it was held in Tokyo and it was a very grand funeral that we could witness.
We had thought we would cheat the music company and stealthily copy the music onto our desktop. But it seems that it is not to be.
Whenever you are dragging and dropping or trying to copying the tracks directly from the CD to your hard drive, what will happen is that they will only copy the shortcut, they won't copy the data. But unlike in a Windows system, in a Mac system, you can actually copy the entire data. For example, here if I want to copy track number 1 and track number 2. So I just copy it and I paste it here. It's already pasted, I have already done it earlier. So track number 1 and 2 we have in this folder called ACD. So this track number 1 is opening. Now let us try and hear it. There are different types of file formats. The first, pulse code modulated, the digitized files which are there are actually uncompressed and they take up a lot of space. So the size of this file, as you can see, is 102.7 megabyte. Now what I will do is I will try and open a software in which I can convert the uncompressed file into a compressed file format, which will take up a lesser space, and we will kind of analyze the space that the new file takes up. Go to the file, export using, we will convert it for the iPhone in order to convert it. We will name it converted, we will just converted and then use the same folder and save it. So automatically it gets converted and it takes a certain amount of time. Now we can see it is using the M4V file format. It is a compressed format, it's MPEG-4 file format, and let's see if we go to the info, we will see that the file has been reduced to 10.6 MB, and if you originally check the original one audio track, the size is 102.7 MB. Now how will it fare if we play both of these files in a music system? Let's listen to the original track first. We will go to the end where we have that was the uncompressed file, and let us play the compressed file now. Play with the same player. You can almost not make out the difference between the two files, although the file size has been reduced to 1/10 of its original size, but the quality is almost unaltered. Now the most common lossy format that is much in use today is the MP3, which has been actually, which is mostly the file format that you hear when you are listening to something over the internet. It almost reduces the data size by 1/10, even by 1/12 in certain cases, and it does a very interesting encoding, so that the end product, there is a little loss in the sound quality, but most of it is there. There are other also compressed lossy formats, for example, the real audio, the AVR or the ATRAC, which was first introduced by Sony in its format called the mini disc, which was also a transitory format. Now in case of lossless compressed formats, we have many, there are many, but mostly in use there is Windows Media Audio, or WMA in short, AAC, OGG Vorbis, and also the newly developed ATRAC compression, the ATRAC 3, which is a compressed format, but it is a lossless compression that they are using.
শসা বিক্রি হয় কি হয় 5 টাকা পিস হয় দিনে কতটা বিক্রি হয় বেশি হয় না খুব কম 10 কিলোর মতো This is a Sony Handycam. It records in this flash drive. Its memory space is 4 GB. It also has a 4 GB internal memory, and it has 3 recording modes: SP, LP and HQ.
Digital technology allows us to create or splice files as small as 2 bytes and embed them with text files or image files or any other medium.
Ukraine.
Using digital technology, it is now possible to make an audio collage where each component of the collage is merely a split second in duration.
The possibilities are practically infinite, waiting for the creative mind to tap them and create sound, the kind of which has never been heard before.